I'm François Schmidt, Research Director at CNRS, and this is a short talk about homogeneous turbulence in the field of marine sciences. So when we speak about homogeneous and isotropic turbulence, we mean the following properties. So homogeneous means that we have the same statistical properties in all points. So it means we are far from boundaries. Isotropy means we have the same statistical properties in all directions, and we assume also that we have in a fully developed turbulence regime, so we have a large Reynolds number. So this is an example of a direct numerical simulation of homogeneous turbulence. So here you have an example coming from the web of a cut of a 2D cut of homogeneous and isotropic turbulence. So it shows that in fact snapshots can be inhomogeneous, but what we mean with homogeneity is that in statistical in time are the same in all points. So we have the concept of Richardson cascade. So Lewis Richardson, in a book in 1922, proposed a few sentences that are now very famous. And he said that big rolls have little rolls that feed on their velocity, and little rolls have lesser rolls, and so on to viscosity. So now it's called as Richardson cascade. And the idea behind it is that we have an injection of energy at large scales. Then we have a cascade from different eddies to smaller eddies, and this is going on until viscosity scale, where you have the dissipation of energy into heat. Later on, it was formalized by the mathematician Kolmogorov in 1941. We proposed the hypothesis that we have universality of fluctuation in the range of what we call the inertial range. So it means the range of scales between injection scale, which is a large scale, and dissipation scale, which is a small scale. So as his assumption was that the statistics depend only in this range of scales on dissipation and scale. And I don't give the detail, but I give only the result, which is obtained by dimensional analysis. So dimensional analysis means, in fact, that you need to have the same dimension in the left and in the right. And on the right, you assume a product between different quantities, and then you obtain the exponents, which are given here. So these exponents correspond to what is called Kolmogorov 41 law, and it means that the fluctuation of the velocity depend on the power 1/3 of the scale, and it's also proportional to the 1/3 power of the dissipation. Using this, also, I don't give all the details of the method, but using this, we can obtain, in fact, the smaller scale of the cascade. And this is now called Kolmogorov scale. And it's written in this formula. So it's a nu cube divided by epsilon, everything at the power 1/4. So I recall that nu is the viscosity, so it depends on the fluid, and epsilon is the dissipation, and it depends on the flow. And when we have these two quantities, we can compute eta, which is this smaller scale of turbulence. So if we show this picture here, we can see the Kolmogorov scale, and in fact, the Kolmogorov scale is of the order of the millimeter, and it separates viscous flow from turbulent flows. So it means that below this scale, we have a viscous regime, and above this scale, we have turbulence. So the order of magnitude, as I say, is the millimeter. And globally, in coastal flow, it's smaller. It's of the order of 0.3 millimeters. And in the deep ocean, it's closer to the scale of the centimeter. So this gives a given picture, which is called the Richardson-Kolmogorov energy cascade, where we have injection of energy at a given scale. We have a cascade of energy and dissipation at a small scale. A last point, which is also important in our application, is the concept of a Bachelor scale, which was proposed by George Bachelor. The idea is to say that for a scalar which is advected by the flow, there is another scale which is important. So you can construct the scale by using the diffusion coefficient, which is D, and by considering the ratio of the viscosity to this value D, which is called the Schmidt number. And when this number is larger than 1, then we have a new scale, which is now called the Bachelor scale, which is the Kolmogorov scale divided by the square root of the Schmidt number. And as an example, when I give here some numerical application, so when the D is of the order 10 minus 9, so we have a Bachelor scale which is about 30 times smaller than the Kolmogorov scale. It means it can be of the order of a few tenths or hundreds of microns. So it will be, it's important also for application to phytoplankton. So finally, the outline of all these ideas, I just to remind the different numbers, we have the Reynolds number, we have the viscosity, we have the diffusion of passive scalar, we have the turbulent kinetic energy, the dissipation of scalar variance, dissipation of kinetic energy, and then we have Kolmogorov scale and Bachelor scale. So all these numbers can be useful to characterize the turbulent flow. So that's all for this short presentation about homogeneous turbulence.